Good afternoon, everyone. In the previous lecture, we just discussed about the bootstrap methods, and we just give the introduction of the bootstrap methods in regression. So we will discuss all these things in the detail. So when we discussed about the bootstrap methods for regression analysis, so we just discussed there are two methods. One is the paired bootstrap, where we just generate the xi and yi pair. All right. And another method was for the residual resampling, where we generate the error term epsilon I. All right. So first we just discuss about the case resampling of paired bootstrap method. So in this method, what we have done, suppose we have the regression model here. Suppose we have the simple linear regression. Simple linear regression model, that is yi equals to beta naught plus beta 1 xi plus epsilon I for all I goes to 1 to up to n sample size. Okay, here we assume that here we assume that xi and yi are IID. Okay, xi and yi are IID distributed independently and identically distributed with some joint distribution f. Okay, and no further assumption we are going to assume about the error distribution or the form of the conditional mean that are required for the paired bootstrap. It is completely non-parametric after that. All right, so in that one, in the first step, what we are going to do, we are going to fit the original bootstrap regression model for the given data set x1, y1, x2, y2 up to xn, yn. We will fit the first model, we will fit the regression model given in equation 1, and we find out the point estimates of beta naught, and that is beta naught cap, and beta 1, that is beta 1 cap. These estimates we will get by using the ordinary least square method. Okay, by using ordinary least square method we use to find out the estimates, and these values we usually use in the practice if we are not bootstrapping, but in the bootstrap they are not directly used to resampling, but they are, we will keep it for the comparison. Okay, we will keep them for the comparison, and then after that what we do in the second step, we will generate the n pairs of the samples xi or bi with replacement. All right, and means we will generate x1 star b, x2, sorry, x1 star b, y1 star b up to x n star b, x, sorry, y n star b we will generate. All right, and b will take the values 1 to up to b. So B samples we will get. All right, so for each sample size, we will fit the regression line again, and we find out the estimates of beta naught and beta 1 again. Means it will be like this: x1 star 1, y1 star 1 up to x n star 1, y n star 1. This will be our one sample, and we will fit the linear regression line for given this data set that we have in equation 1, and we find out the our beta naught cap 1 and beta 1 cap 1 from here, and then we generate the another sample that is x1 star 2 y1 star 2, okay, and so on up to xn star 1 yn star 2, second sample, that we will get the another beta naught cap 2 and beta 1 cap 2, these estimates, and so on up to b time we will get it. And after that, by using the ordinary least square method again and again, we will generate estimate these estimates b number of times, capital B number of times. After that, we use these inference beta 1 star 1 beta cap star b. You can put the star here, okay, star b for the inference. All right, in that one we can find out the inferences like bootstrap standard error. For the bootstrap standard error, the formula is of beta 1, sorry, bootstrap method error beta 1 cap, it will be equals to square root of 1 upon b minus 1 summation over the range of I goes to 1 to capital B. All right, beta 1 cap star I minus beta 1 cap star bar. All right, and whole square of that one. So where beta 1 cap star bar, it is the mean of those estimated values that we got from here. All right, that is 1 upon b summation over the range of I goes to 1 to capital B beta 1 cap star I. All right, so this is a non-parametric estimates of the standard deviation of beta 1. Okay, this standard error of beta cap is the non-parametric estimate of the standard deviation of the beta 1. Similarly, we can find out the percentile confidence interval for beta naught and beta 1 by given 2.5 and 97.5th percentile. Okay, percentiles of beta 1 cap star I. So we can generate this interval, percentile interval of the 95% confidence interval. This interval is based on the idea that the bootstrap distribution approximates the sampling distribution, so it quantiles can be used directly, and bias also we can find out after that. The bias will be equals to beta 1 cap star bar minus beta 1 cap. Okay, this beta 1 cap is the estimate that we find out for the original data set, for this data set. this beta 1 cap that we find out in the initial stage. This is the same beta cap 1. All right. So this is the bootstrap for regression for the pairs. All right. So here some advantages are there for this resampling method. That is the non-assumption for the error distribution handles the heteroscedasticity. The variance can depend on x only. Random x means valid when x is stochastic, and robust work even with the model is misspecification. So there are two assumptions is there for this model. Okay, the assumptions are, first assumption for this method that we should follow. First is that the pair xi and yi are IIDs and follow some joint distributions. Okay, both are IIDs and follow some joint distribution of xy. Okay, these assumptions fail when we use the time series data or cluster data or any setting with the dependency, all right, between x and y. And assumption two that we have, it is that the statistic of the interest, the statistic of the interest, here we have the regression coefficient. Okay, regression coefficient is a smooth function of the data. That is the second assumption that you should have. For the regression, this holds under the standard regularity condition. Okay, but we have the limitation here. The limitation that we have, the paired bootstrap is sensitive to the distribution of x. If there are influence points in x, they may appear too often or not often enough in the bootstrap sampling. Okay, and that will inflating the variance. So it does not assume a fixed x. It treats x as a random variable. If x is truly fixed by the design, the residual bootstrap may be more appropriate in that condition. So after that, we will move to the bootstrap method for the residuals. What is it? So in that one, the resampling of the residual, not the pairs. Okay. So in many experimental settings or real life situations, the predictor x are fixed by the design, and the only randomness comes from the error epsilon I. Okay, it comes from the epsilon I. So the residual bootstrap leverage this structure by keeping x fixed and resampling the residuals. So in that one we obtain the method will be algorithm will remain that we fit the original model for the given data as we have done in the paired one. Okay, so fitted the values represents the estimated symmetric part, so it will remain same. In the second part, what we will do, second stage, the residual are observed. Okay, that is the counterpart of the true errors, so they contain the information about the error distribution here. Okay, after that, in the third part, we are going to center the residuals. Here we are going to center the residual. Step 3 is this is the important part. Okay, why we are doing it? See, by the construction, ordinary least square residuals may have the zero if the model includes an intercept. Okay, but however, in the finite sample, the mean may not be exactly zero. as when we have the real life data set. So due to the numerical issues, or if the model is misspecified, because in the real life situation, whenever we have the data, so and we fit the regression line, it never happens that it is exactly fits always. Some fluctuations we find out and some misspecification we find out. So because of that, mean is not always zero. So centering the centering the residual with respect to the mean of the error, it ensures that the bootstrap errors have the mean exactly zero, which is necessary because the true errors are assumed to have the mean zero. Okay. So what is the effect will happen when we are going to take it zero? So the centered residual epsilon I curve have the mean zero and the same variance as the original residuals have. So they form an empirical distribution with mean zero, which we will use as a proxy for the true error distribution. All right. So that's why we are doing the centering in our model here of the residual. So after that, we draw n values from the empirical distribution of centered residuals. All right. And this represents the drawing errors from the unknown error distribution, because we sample with replacement. So some residual may appear multiple times and others not at all will appear. So reflecting the randomness of the error. So after that, in the second part, after that, second stage of the fourth step, this new response of the bootstrap errors will construct the new model that will be yi star equals to yi plus epsilon I star. Okay, here yi cap is fixed since x is fixed and beta is fixed from the original fit. All right. So the only source of randomness is the bootstrap error, that is epsilon I star here. Okay. This construction assumes that the true model is yi equals to yi cap plus epsilon I. Okay. It assumes that the true model is yi is equals to yi cap plus epsilon I. It means that the estimated mean function is corrected, and if the model is misspecified, this step will generate the data from the wrong structure. All right. After that, in the third part of the fourth step, we fit the regression model. Okay. So we regress the bootstrap response y star on the original x, and this will give us the new coefficient of the beta cap star b. Okay, when you will use this new y here, x is going to be fixed, but y, the new y will be yi cap plus epsilon I. All right. So the variation across the b comes slowly from the resampled error. After that, we record the all the beta cap star b for each sample here, and we find out the inference as we have discussed earlier, the same one that we discussed, that is biasness. Similarly, we can find out the biasness. Similarly, we can find out the confidence interval, and similarly, we can find out the standard error. Okay. So this is the model for the residual bootstrap method. So here we have the again two assumptions for this model. First assumption for this model, assumption for residual bootstrap. Okay, so the first assumption is that the regression model is correctly specified. The regression model correctly specified. That means the expected value of y for given x, because we are assuming that y is fixed, sorry, x is fixed, and we are going to generate the y through the error term that is exactly equals to beta naught plus beta 1 x. All right. And second assumption that we have, that is the error term, the error epsilon I is IID with mean 0. Okay, they have the distribution, some distribution, and where mean is 0 and variance is constant. Okay, variance is constant, say sigma square. Okay, because of the homoscedastic condition, this assumption is very important here, because resampling the residual ignores any structure in the variance. All right, we are not going to assume any structure for the variance here, we are assuming it is constant. So the limitation of this model is that if the errors are heteroscedastic, means variance is not constant for all epsilon I, okay, for all I, it is not constant, at that time this will be invalid, because of the variance of epsilon I may depends on xi, and the randomly reassigning the residuals, okay, that will destroy the dependency. So this method is sensitive to the model misspecification. If the true relationship is non-linear, the residual will reflect that, and the resampling them will produce the unrealistic bootstrap sample. All right, so these are the assumptions for this model, and this is the limitation that if the variance is not constant at that time, it will be problematic. Okay, so okay, here we have the comparison of both models, that is random case sampling. In the case resampling, assumption for the x is that in the case resampling x is random. In the residual resampling we are going to fix it, and heteroscedasticity, in the case resampling it is robust, but in residual resampling it is sensitive, because we are assuming variance is sigma square, that is constant. And in why we are saying robust in that one case resampling, because we are generating x and y both again and again. So in that case x is also going to change every single time, so variance of the error will change every single time. So model misspecification, that will be robust, and here again it will remain sensitive, okay, because we are not generating the x in the residual resampling. Efficiency, the efficiency of the case resampling is lower in compared to the residual, okay, because in that one we are not giving any weightage to the, in the case resampling we are not giving any weightage to the error term, okay. So preserve x design, there is they don't there is no need to design the x in the beginning in the case resampling, but in the residual resampling you need to fix it, okay. In the leverage point extreme points, in the case resampling it can dominate, because if x has the extreme values or the outliers in the data set, so it will occur every single time when you are going to generate the sample with replacement. While in the residual resampling we are going, because we are going to fix them, so it will not be any issue at that time, okay. So case resampling is a default choice, especially for the observational data, and residual resampling when the you trust the model and have the fixed design. So that is the practical recommendation for these two models. So here we are going to take one example for the simple linear regression. So data is given, that is advertising spent in X and the sales in Y, and N is equals to 30 on the 30 stores it is given. So suppose the estimate for the real data set, suppose the estimate of beta naught is 5.2 and beta estimate of the beta 1 is 0.85. See, this is beta naught cap, this is our beta 1 cap. Okay. And the classical standard error is 1.15, 0.12 respectively. And we find out that both of them are highly significant because the p-value is 0.0001. That is smaller than 0.05 or 0.025. So at the 5% level, both of them are significant. So here we have the R code. We just check it, how it will work. Okay. On the R programming, we check this one. So here we have this code for our given data set. So here we generate the X from the uniform distribution. Okay, we use the set.seed to generate the resampling, and because in the question we assume that we have the 30 stores, so we are taking n equals to 30 here. Okay, so we need the 30 observations here. So X is generating n random numbers, means 30 random numbers from a uniform distribution between 10 to 50. Okay, here X is the mean to represent the advertising spend as a predictor, and Y is the response that we had, that we are taking 5 plus 0.85 into X and plus R norm and 0.5. Okay, so we create the response variable here in this line, in this equation. Okay, of the sales as a linear function of X plus the random error, and the true underlying model is as I told you, that is Y equals to 5 plus 0.85 plus X plus the error term. Okay, so 5 is the intercept and 0.85 is the slope of X, and 0.5 adds the independent normal errors with the mean 0 and the standard deviation 5, and we fit the regression model Y equals to X here. Okay, we check it. So what is X? This is our X, this is our Y. Okay, so this is our original data set of X. This is our original values of the Y after fitting the model, and after fitting the original model we got the intercept 8.94 and well slope is 0.733. Okay, so original coefficient we will check here. So we extract the coefficient of the original fit that we got similar. All right. Now what we are going to do, we are going to set the resampling of 5000 here. All right. That define the number of bootstrap samples to draw. We are taking here 5000 because the large number ensures the stable estimates of the standard errors and the percentiles. So before that, we are defining or create some matrix of capital B rows and 2 columns here. All right, that is the filled with the NA, that is the null matrix we are making here. Each row will store the intercept and the slope for one bootstrap sample. All right, so after that we just run this loop for B in 1 to B. Okay, and we are going to generate the samples 1 to n is equals to 30. So we draw the bootstrap sample that indicates from 1 to n with replacement. This means the original observation may appear multiple times, other not at all. All right. And after that boot fit, we are fitting a linear regression by using the resample data, okay, in Y IDX and X IDX. Okay, preserve the original pairing of X and Y. Okay, and in the boot coefficient, we are storing the intercept in the first column, and in the second column, we are storing the slope from these bootstrap fit in the corresponding row of the boot coefficients. All right. So this one we will run. Okay. Now here we call the original model, and then we call here the boot standard error, and after that 95% quantile confidence interval of the model for the coefficients, okay, at 95%. So in the original model, the beta naught was 8.946, and the beta 1 hat that we got, that was 0.734. That was a little bit far from the original model that was 5. Okay, because original value of the beta naught was 5. Here we had 8.94 in the simulated one, and beta 1 was 0.85, but we had 0.73. After bootstrapping, it is reduced. The standard error that we got, that was the 3.123 of the standard error of the model, and 0.083 will be the standard error for beta 1. Okay, we just try to call this matrix. See, this is the matrix, right? And you can find out the mean of that one, of both of them. I just try it, whether I'm right or not, I don't know. I check it, mean of bootstrap coefficients. What is the name of the column here? Comma 1, comma 2. Okay. Comma 1. 8.96 and second column's mean is 0.73. So it is approximate the same that we had for the given data set that we got. All right. So this is the R code for your bootstrap for the simple random sample for the paired data. All right. Now we will go for the bootstrap for the residual. For the same model, we will go for the bootstrap for the residual. So here we use the same model that we had earlier. X and Y will remain same. All right. That we had 0.8.9456 and 0.7338. And we just check the fitted value of the original model. For that one, the command is fitted. Okay. This is the fitted values of the Y. All right. For each observation. So this is the fitted values. Now we are going to, after that, we find out the residuals of the original fit model. Okay. It will provide us the epsilon I minus epsilon I cap. Okay. Wait a second. residuals. So this is the residuals that we got. Okay, epsilon. Sorry, this will give us the residuals epsilon I, that is equals to yi minus yi cap, and after that we are going to center the our residuals by using residual minus mean of the residuals. All right. So this is the centered value of the residuals. Okay. So if you just check what is the mean of the residual here, mean of the residual is 3.75 e raised to the power minus 18. Okay, this is not the exactly 0, but it is near to 0. All right. So as I told you in the beginning that it may not be 0 because of the data, generated data or real life data. So that's why we need to center it. Okay, our residual. If you want to find out the mean of this one, centered residual, let's check what is the mean of that one. Mean of the centered residual. Okay, it will be the same, but it will help us to find out it to keep it 0. Okay, right now in the next step, what we need to do, we need to take the residual that is 5,000. Oh, sorry, we need to take the bootstrap resampling that is 5,000, and for the bootstrap confidence coefficients, we make another null matrix of row of size capital B, that is 5,000, and the columns, that is 2. So beta naught and beta 1, it will keep both of them. All right. So after that, we are going to apply the for loop to resample the residuals. All right. In the boot residuals, we are going to generate the random sample of the from the centered residuals of size n and with replacement. All right. And then we create the bootstrap of the y. Okay, that is the y star equals to the fitted values plus the bootstrap residuals. All right, it will create a new response vector of new create. It will create the new response vector by adding the resampled residuals to the original fitted values. All right, the design matrix X remain unchanged, so the same X values can use in every bootstrap iteration. This step assume that the model from linear with intercept is correct, and that the errors are IID. Okay, so after this one, we just go for the boot fit. So we will apply the linear regression model. Okay, with the ordinary least square method. And here just remember one thing, that X is the original predictor, that is not resampled, this X. All right. So after that we will call the coefficients of the fitted bootstrap method, and we will store them in the matrix. Okay. Now after that we call the residual of the standard error of the residual bootstrap by applying the command round apply boot coefficient residuals. Okay, comma 2, comma hd, comma 3. All right, so apply boot residual coefficient here, comma 2, comma hd, computes the standard deviation of each column, intercept and slope across all the bootstrap replicates. These are the bootstrap estimates of the standard errors of the coefficients, and the results is rounded to the three-dimensional places and printed with the descriptive label. Okay, that's why we use the 3 here. And in this one, in the next command, in the cat, in the boot coefficient, that one confidence interval, here we use this command, boot coefficient residual comma 2. All right. It will extract all the bootstrap slopes estimates and the quantile of this entire command with C 0.025 and 0.975. It will give us the 2.5th and 97.5th percentile of these estimates and forming a bootstrap percentile bootstrap confidence interval for the slope, and the interval is rounded up to the 3 decimal and printed, and n added here. The slash n is add a new line before the output for the cleaner formatting. All right, so here we will call both of these commands. So it gives us the residual bootstrap standard error for the beta node is 2.625, and for beta 1 it is 0.075, and the 95% confidence interval for the slope is 0.586, and for lower limit is 0.586 and the upper limit is 0.88. All right. So this is your R code for residual bootstrapping methods. Okay. Now comes to the multiple regression bootstrap. In the multiple regression bootstrap, everything will remain same. Okay. As the simple linear regression, instead of generating x and y, x1 and y1, you will generate the x1, x2, x3, whatever the estimates are, whatever the coordinates are there with the y. Okay, means here we have the beta node, beta 1, beta 2, beta 3. So we need to generate here x1 I1, okay, x2, sorry, xi2, xi3, and yi. We need to generate these pairs. Okay, for all I will go 1 to up to n. We need to generate that one. So they have given us a model where the house prices are given, that is price is beta node plus beta 1 into the size of the house plus beta 2 into the number of bedrooms in the house plus beta 3 into the ages, means how old it is, the build house, how old it is, plus the error. Okay, this is the model. In that one we got the intercept is 50,000, suppose classical standard error is 1500, size of the house in the square feet is 120 and with the standard error 15. Okay, bedrooms are estimated is for beta 2 is 8500 and the classical standard error is 3200, and the age with the estimates of beta 3 cap will be minus 1200 and the standard error is 400. Okay, so are the question is that Bootstrap question are classical standard errors are reliable with the non-normal errors. So what we are going to do here, we are going to apply the R code again here. So here what we are going to do, in this code, we are going to define n equals to 100. Okay, number of observations that we are going to take and the size. In that one, we generate the 100 random numbers from a normal distribution with mean 1800 and the standard deviation 400. This variable represents the floor areas of the houses in the means in the square feet. In the bedroom, we are generating a sample from 2 to 5, okay, of size n with replacement true. It means this command is basically explaining the we are randomly drawing the n values from the integer 2, 3, 4, 5. This create a discrete predictor for the number of bedrooms. All right. And after that, we generate the age from the uniform distribution of size n 1 to 50. All right. So here we generate the 100 random numbers from a uniform distribution between 1 to 50, representing the age of the houses in the year. All right. After that, we are going to introduce our model, that is price equals to 5,000 plus 120 into size plus 8,500 into bedrooms minus 1,200 into age plus r known n comma 0 comma 20,000. Means construct the response variable price according to a linear model. Okay, intercept is 50,000, effect of the size is 120 per unit, and effect of the bedroom is 8,500 per bedroom. Effect of the age is 1,200 per year. Okay, that means in the negative, it means older houses are cheaper, and then the random error. Okay, it adds the independently normally distributed error with mean 0 and standard deviation 20,000, representing the unobserved factor affecting the price. All right. So after that, we are making a one data frame here. In this data frame, we are assembles the four vectors: price, size, bedrooms, and the age. Okay. Then we fit the model original, that will be our original fit from for the given generated data from the for the size, bedrooms, and age. So we just check it. What is it right now? So original fit, age, it give us intercept value is 3,800. Oh, sorry, 38,073. Size is 125.9. Bedrooms are 9,400 408.8, and the age, with respect to the age, the coefficient value is minus 1206. All right. So after that, what we are going to do here, we are going to resample 5,000 times. All right. And again, we are going to create a one matrix of size b by 4, means 4 columns for price, size. Okay. Sorry. Yeah. Price, size, bedroom, and age. All right. And b is the number of rows that we needed. 5,000 rows we need, and then we apply the for loop. Okay, in this for loop, in the IDX, we are going to generate the sample from 1 to n, okay, of the size n with replacement. All right, in the boot data, we generate the data of size IDX, means that is the index. Okay, and the boot, in the boot fit, we are going to apply the uh, linear regression model. All right, and in boot coefficients, we are going to store the coefficients of the bootstrap regression model. All right, and we will compare the standard classical standard error that we will can compute by the command summary of the original fit dollar coefficients, okay, of all the covariates, and the boot standard error, we just apply the apply command with the boot coefficients comma 2 comma standard deviation. Okay, here 2 we use for the columns, and if you write 1, it will apply for the rows. All right, and in the C bind, we are going to combine both standard errors, classical as well as Bootstrap. So we will check what it will be. Okay. In the classical, the intercept standard error was 10,961, but in the Bootstrap it was 12,000. In the classical, the size standard error of the size coefficient is 4.93, but for the Bootstrap it is 5.02, and for the bedroom it is 1768.61, and it is 1692 for the bedrooms. So it reduced here. And for the age, it is almost similar, 136.46 and 136.29. The error in the Bootstrap will reduce if you are going to put the set on the set dot seed. You are going to remove the set dot seed, and you will increase the sample size here, and you will increase the resampling size from 5,000 to 10,000 somewhere. So it will reduce. All right, because sample size becomes a very big problem here, or the resampling size becomes very big problem when you have the multiple covariates. All right. So that is the R code for your multiple regression coefficient. Okay. Till now, do you have any doubt? Do you have any doubt here till now? Should we proceed? Anybody has any doubt? Okay, so we just move to the wild bootstrap. Okay, for heteroscedasticity. All right, so the wild bootstrap was developed to handle the heteroscedasticity while retaining the fixed X structure. Okay, when the variance depends on X, but the structure of the X is fixed. All right. So in that one, classical standard errors are wrong. Residual bootstrap fails. Assume the constant variance, and the case resampling works, but is less efficient. So basically, when heteroscedasticity is there while retaining the fixed value of X structure, so we use the wild bootstrap method. Instead of resampling the residuals, it transforms each residual by a random variable, preserving the variance at each xi. Okay, so we are going to use the transformation here in this method. So this is the wild bootstrap solution. Instead of resampling the residual, transform them epsilon I star equals to epsilon I cap into Vi, where Vi is the random variable with mean 0 and variance, expected value of Vi equals to 1. So the random choices for Vi is the two distribution, Rademacher and Mamin. These are the two distributions that we assume in the wild bootstrap. So we just understand it, the algorithm. Okay, algorithm I gave? No, there is no algorithm. So I just give you the entire algorithm. So what is there in the algorithm? Wild bootstrap. algorithm. So in the wild bootstrap algorithm, the first step will remain similar to the regression models, that is fit the original model, that is your yi cap equals to beta naught cap plus beta 1 cap xi. Alright, and compute the residual. In the second step, compute the residuals, that is your epsilon I cap is equals to yi original data minus the fitted values of the yi. Alright, for given beta naught cap and beta 1 cap. And in the third step, what you need to do, for b equals to 1 to b, small b equals to 1 to up to capital B, that is equals to maybe 10,000. Alright, for each I, okay, for each I, generate a random variable vi, a random variable generate a random variable vi independent of the data. Okay, it should be independent of the data. Okay, such that expected value of vi is equals to 0 and expected value of vi square is equals to 1. Okay, then create the bootstrap error. In the second part, create the bootstrap error. Okay, that is epsilon I star is equals to epsilon I cap into vi. Okay, now you are not going to subtract it, you are going to multiply with the yi. In the third step of your third stage, create the bootstrap response. Okay, create bootstrap response. Okay, that will be yi star equals to yi cap plus epsilon I star. And in the fourth part of the third step, put the regression of y star. Okay, put the regression of y star or on the original x to obtain beta cap star small b. All right. And then in the fourth step, use the estimated beta 1, sorry, yes, beta 1 star 1, beta 2 cap star 2, sorry, beta 1 cap star 2 up to beta 1 cap star B for inference. All right, that will be your model. All right, here you know that if you just see, we were saying that generate the random variable vi. Okay, that should be independent from your given data. So here we have mentioned two distribution, Retimeter distribution and Mamin distribution. Okay, so these are the two distribution that we are using here in the bootstrap. So Retimeter distribution was given by a German mathematician. Hence Retimeter. So this is that. I just give you the introduction of that one. And so distribution. Okay, it is given by the Hans Remnicher. So this is that a random variable v follows a Retimeter distribution. Okay, if it takes the values -1 or +1. Okay, so in that one, v only takes two values, that is -1 or +1. All right, with equal probability. This node belongs to that is equals to with equal probability. All right, means probability that we will take the values +1, it will be 1 by 2, and probability that we will take the value -1, it will again 1 by 2. All right, so why we use this distribution here? Why we are saying? Because this distribution has the key property that expected value of v is always 0 and expected value of v square is 1 and expected value of v raised to the power 3 also 0. So that is suitable for us. Okay, so that is the one distribution that we use, and another distribution that we had, that is the Mamin distribution. It was published in 1993. Okay, and it was given by the Eno Mamin. Okay, 1993. It was published. So this model is basically known as the golden selection for the bootstrap because the appearance of the golden ratio in its values. So basically the definition of it is, says that a random variable v follows a Mamin distribution. Sorry, capital M. Mamin distribution if v is defined as v takes two value. One is 1 minus square root of 5 divided by 2, that will be approximately 0, minus 0.6180 with probability 5 plus root 5 divided by 10, that will be approximate to 0.7236 and Another value we take 1 plus square root of 5 divided by 2. That will be approximate to 1.6180 with probability 5 minus square root of 5 divided by 10. That will be approximate to 0.2764. So total probability will be 1. Again, the key property of this distribution is expected value of V is 0. Okay, and expected value of V square is 1 and expected value of V raised to the power 3 is 1. Alright, so this is the key property of this distribution. So that why we are using this distribution to multiply with the error here. Okay, when we are saying we need to multiply these variables with the error, why we are saying it? Okay, so the choice of this distribution of Vi is not arbitrary. The wild bootstrap works because it represents the first two moments of the original error distribution. Okay, consider the bootstrap error, that is epsilon I star equals to epsilon I cap into Vi. Alright, the conditional on the original data. So the first point is that why it is useful the conditional mean, that is the expected value of epsilon I star for the given data. Okay, it should be equals to epsilon I cap into expected value of Vi. Alright, so if you will take any variable Vi in the form of Vi, that if its mean is not 0, so at that time the mean of the epsilon I star will not be 0. But we have the assumption that the mean should be 0 for the error. Okay, so that's why we need to take expected Vi in such manner. So expected value of Vi should be 0. So the entire mean will be 0 because epsilon I cap into 0 will be 0. So it will hold that one. Okay. So for the bootstrap error to have the mean 0, okay, that is the standard regression assumption we required. Expected value of Vi is 0. So both uh, Radimcher and the Mamin distribution satisfy this one. And second, the conditional variance. So the what is the conditional variance here? If you will say the conditional variance will be expected variance of epsilon I star given data for the given data is equals to epsilon I cap whole square into variance of Vi. Okay, so for the bootstrap variance to correctly reflect the original residual variance, so in that case we need to require the variance of Vi should be equals to 1. Okay, so both that is Redemption and the Mamin satisfy this as well. Okay, so both distribution are valid first order approximation because they meet these two fundamental criteria of our bootstrap methods. All right. When we use this one, we use the Redemption when distribution is symmetric. Okay, and Mamin we use when the distribution of our model is asymmetric. All right. So at that time we use this model, these two models. Here one thing is there. Someone may ask that why we are not taking Vi follows normal distribution with mean 0 and variance 1. That also can be fulfilled. It can also work, but it introduces the continuous randomness that may be less efficient in the small samples. So that's why we don't use Vi follows the normal distribution with mean 0 and variance 1. We use the Redemption and the Mamin distribution for the wild bootstrap heteroscedasticity. Alright. So this was the model for us. Okay. And here the comment should be here how it will preserve the heteroscedasticity. So consider the conditional variance. Okay, for the bootstrap error, so it will be variance of epsilon I star for the given data xi and error epsilon I cap. So it will be equals to from this one epsilon I cap whole square into variance of y vi equals to epsilon I cap whole square. Right. Since epsilon I square is a consistent estimator of the sigma square. Okay. That is the variance of uh, sigma I square. That is variance of epsilon I for the given data with the given data xi. So the bootstrap error inherent the heteroscedasticity structure. So observations with the larger residual indicate the larger variance will continue to have the larger variance in the bootstrap samples also. Alright, so here we have two assumptions again for this model. So first assumption is that the regression model is correctly specified for the mean. Okay, and the wild bootstrap only addresses the heteroscedasticity, not the model specification. Okay, it means the regression model is correctly specified for the mean. Okay, and second is that second assumption the error are independent with mean zero. The errors are independent with mean zero. Okay, but the variance may depends on xi. Okay, so there is also a limitation for this model. If the model is misspecified, the errors are not pure errors. Okay, so residuals are not the pure errors, and multiply them with vi will not correct the bias. So the choice of the vi distribution can affect the finite sample performance. So redemption is often preferred for symmetric and the simplicity here. All right, this is the limitation for this model. Now we will go for the R code of the wide bootstrap method. Okay, so here in the wide bootstrap method, we are using the redemption distribution. So here we create or define a function named wild bootstrap that takes the three arguments. First is x, the predictor vector. Okay, predictor vector x, and it assumed to be a numeric vector, and y. Okay, that will be the response vector, and the length of the y should be remain same as x, and b is the bootstrap of the replicates defaulting up to the 500, oh sorry, 5000 replications. Okay, inside this function we are introducing the n, that will be the length of data set of y or x, and then we apply the model here, fitted model, y linear regression model, and then in this one. After that, we call the fitted values as the same earlier that we did, and after that we will call the residual, all right, of that model. And in that one we call the bootstrap. After that we will create a bootstrap coefficient matrix of size b equals to b will be the size of the resampling and 2 is the beta node and beta 1. In that one we just call the Rademacher weights, Rademacher distribution. V is the sample we are going to take between from -1 and 1. All right. The set of the observation is -1 to 1 only here, and with the equal probability. And these are the wild bootstrap. These will be called as the wild bootstrap weights. And after that we calculate the wild residual. So that will be residual into V. After that, in the Y star bootstrap, we just construct a bootstrap response of the Y star by adding the wild residual of the original fitted values. Okay, and the predictor X remain unchanged. The wild bootstrap is the residual based method that conditioned on X. After that, on the boot fit, we are going to fit a linear regression to the bootstrap data X comma Y star. All right. And then in the boot coefficients B equals to coefficient of the boot fit, we store the estimated coefficient, intersect and the slope from this bootstrap fit in the bth row of the boot coefficients. All right. After that, we close the loop and we call the results of the bootstrap method here. Okay. These are the results. The results that we took here, we took for the first problem of our simple regression. Okay. X and Y. So this is the results, wild results for our first problem. All right. Do you have any doubt in this one? Anybody has the doubt in this one till now, or should we proceed? Anybody has any doubt in this one? Wild bootstrap method. Okay. So this till here we just discussed about the bootstrap regression. So there are the summary of that one. In the case resampling, we resample the X and Y pairs. Most robust works with the random X. And in the residual bootstrap, we resample the residual, keep the X fixed. More efficient require the homoscedasticity. And wild bootstrap, we use the transform residuals with the random signs. Okay, it will handle the heteroscedasticity. So what you can do in further things, you check the residual plots for the heteroscedasticity. If the homoscedastic, use the residual bootstrap. If it is heteroscedastic, use the we can use the case resampling or wild bootstrap and compare the bootstrap standard error with the your classical standard errors. Okay. In that, after that, bootstrap for the hypothesis testing. Okay. So what kind of challenges that we have here? Uh, in the classical test require the non-null distribution of the test statistics, often assume the normality, all right, may not exist for the complex statistics. Okay, so whatever the test statistics you used till now, what are the test statistics we have used? We used, sorry, t-test, z-test, okay, pair t-test, okay, two sample t-test, two sample z-test, chi-square test, okay, and f-test. Here, t-test and z-test we used for the testing of mean, correct? And f-test and chi-square we usually use for the testing of variance, right? Do you study any method, or did you study any method, any test, statistics for testing of median or testing of the correlation or testing of the that one standard errors or standard deviation? Sorry, standard deviation is the variance only. Standard error or any testing method for the mode. Did you study any kind of these methods? Have you seen the test statistics for testing of median or that one standard error or the ratio? Have you seen that? Anyone? Right. Because they don't exist. All right. And in the t-test, when you are testing for the mean, what are the assumption is there? The assumption is that data is normally distributed, means xi follows the normal distribution. Okay. Data should be normally distributed. Then you can use the t-test or z-test. Otherwise, you cannot use that one. It will be difficult. All right. So the bootstrap is the solution. So what we do, generate the bootstrap sample under the null hypothesis and compute the test statistic for each bootstrap sample and compare observed statistics to the bootstrap null distribution, and p-value should be equal to the proportion of the bootstrap statistics as the extreme as possible as observed. So that will be your bootstrap testing framework. So what is the general of framework for the bootstrap testing? That is, we need to define the hypothesis h naught equals to h naught such that theta equals to theta naught versus h1 such that theta is not equals to theta naught. All right. And suppose theta be a parameter of interest and consider we are considering the testing these null hypothesis. All right. And let t equals to tx. For example, t equals to theta cap minus theta naught or theta cap minus theta naught, absolute difference we are taking, or any other statistics we want to compute. All right, and let t observed is equals to the tx observed. All right, and be the its observed values. So after that, we need to define the bootstrap p value. How we will define the bootstrap t value? We compute these statistics, theta cap minus theta naught or absolute difference of theta cap minus theta naught for each generated sample for the parameter. All right, parameter can be anything, mean, median, mode, or standard error or ratio, anything. Okay, under the H note, then what we will do, we will check the probability. Okay, we will check the after generating the B bootstrap test statistics T1 is T star 1, T star 2 up to T star B. Under H note, the P value that will be computed as the P equals to absolute T star B should be greater than equals to absolute T observed value plus 1 divided by B plus 1 for the two-sided P value. Okay. And for the one-sided, it will be, we will remove the absolute sign here, and it will be P equals to uh, T star B greater than equals to T observed plus 1 divided by B plus 1. So here plus 1 is we are adding in the denominator and denominator. That what is the reason behind it? That under the H note, the original sample is also a valid realization for from the null distribution. By adding 1 to the numerator, that is that counting the original statistic as the one of the extreme ones, and 1 to the denominator, that will calculating the total number of the samples considered. We treat the original sample as one of the B plus 1 draws from the null. Okay. So here in the B, we have total number of resampling. When we are adding 1, so what we are doing, we are treating the our original data as the 1. Okay. And ensure P should be always greater than 0, always. Okay. So without the correction, if no bootstrap statistic exceeds T observed, okay, from the T observed, no bootstrap, if none of the bootstrap statistic exceed from that one, we get the P equals to 0. Okay, at that time. That will implying the observed result is impossible under the H note. This is overly confident and statistically incorrect because there is always some positive probability, however small it is. Okay, it doesn't matter, but some probability will be there. So the correction yield will be at that time P equals to 1 upon B plus 1. Okay, even though all these probabilities are 0, means none of the T statistics from the bootstrap is less than T observed. So this will be 0. So even though we will have the 1 upon B plus 1, that will be the value of the P. Alright. So uniformity under H note. So makes the test exact under the H note. P follows the uniform distribution 0 to 1. So for an exact test under H note, the P value should follow a uniform distribution, and plus 1 correction ensure that the empirical distribution of the P value is approximately uniform and avoiding the discreteness that would otherwise cause of the test of the conservative or liberal. So why we are doing this one for the further, if you want to read, you can see the research paper of Davison and Hinckley. Okay, Hinckley 1997. This research paper you can see for the further information. Okay, so how we use the parametric bootstrap test after calculating this p-value. So when we assume a parametric model and want to test the parameters, okay. So in that one, when we are willing to assume that the data comes from a specific parametric family, all right, f theta for example normal, exponential, or Poisson, we can simulate directly from the null distribution f theta naught. Okay, f theta naught. Right. So the algorithm will be like this. So in the parametric bootstrap test, set up the null hypothesis h theta equals to theta naught and compute the t observed from the original data. All right. And after that, for b equals to 1 to b, all right, generate the x star b. Okay. X star b from the given distribution means we must generate the data from the distribution specified the null hypothesis only, not from the f theta naught cap. Okay, whatever the x star b you are going to generate, you should generate from the f theta, the original distribution. Okay, original distribution under h naught. Okay, you should not generate from f theta, f cap theta. All right, that is the thing that you need to remember. For example, if you are testing h naught theta equals to 5 with normal distributions, and that distribution x is basically normal with mean 5 and variance sigma square. So at that time, uh, so after that, what you basically you need to do, if sigma, you need to generate the data again and again from this distribution only. All right. After that, in the third step, we need to compute the theta cap star again and again. So like here, sigma square is unknown in this one. And at that time, we need to generate the sigma square again and again. So we can generate the sigma square of, oh, we can first estimate the sigma square from the original data. All right. And if sigma square is unknown, so we can often use a consistent estimate of sigma square. So this is the parametric bootstrap with estimated nuisance parameters. After that, we compute the theta cap star b from the bootstrap sample and calculate the our test statistics theta t star b theta cap star b minus theta naught, that is the standardized version. All right. After that, we compare with the p-value that we defined in the previous slide. Here we find out the p-value and we will compare it with the h naught. All right. There are two assumptions for this model. This one, hypothesis testing under the parametric. First is that the parametric family f theta should be correctly specified. Okay, the parametric family f theta must be correctly specified. Okay. Second thing is that the parameters, if the parameters are estimated, if parameters are estimated, all right, the bootstrap must account for this uncertainty. The bootstrap must account for uncertainty. All right. So this is the assumption for this one. And now we have the testing, mean testing of the exponential distribution. So here we have the claim component lifetime is 500 hours, n is equals to 25 components we have, and x bar is 475 hours. And the hypothesis that we need to check, that mean is 500 hours or not, or against the alternative hypothesis mu is less than 500 hours. So what we are going to do, in the parametric bootstrap under the H node, we assume that H node that xi follows the exponential distribution with parameter lambda equals to 1 upon 500 and generate the bootstrap sample from the exponential distribution 1 upon 500. And for each sample, we generate the x bar star and we compute the p-value proportion with the x star bar less than equals to 475. So if p-value equals to 0.089, we fail to reject the null hypothesis at alpha equals to 0.05. So this is the condition that we have. Now we check our bootstrap method. Okay, this is bootstrap for two sample, permutation, correlation, non-parametric. Okay, again bootstrap for two sample. Yeah. So what we are going to do here, we have in the X, we are going to generate the simulated data. Okay. So we are generating 25 observations, 25 independent observation from the exponential distribution with the rate parameter lambda equals to 1 upon 475. Okay, so from there, the true mean of the population is 475. Okay, but we are pretending that we don't know this and the test whether it could be 500 or not. All right. So after that, we compute the sample mean. Okay, for the observed data, and mu naught is the hypothesis. Okay, hypothesis mean under the null hypothesis, that is H naught such that mu equals to 500, and the test statistics is chosen as the difference between the sample mean and the null hypothesis value. So that is T observed is basically x bar minus 500. Okay, so test statistics is x bar minus 500, that is your mu naught. All right. And because the alternative hypothesis is H1 such that mu is less than 500, we will look for the evidence that the observed mean is less than 500. That is the negative value of the observed t. Okay, we will look at the observed value of t observed. After that, we just apply the bootstrap with the 999 replication. In that one, what we are going to do, we are going to define the null vector t star b. Okay, that will create an empty numeric vector of length b to store the bootstrap test statistic. All right, after that, we are going to apply the for loop. In the for loop, in the x star, we are going to draw the new random sample of size 25 from an exponential distribution with mean exactly mu equals to 500, since the rate is 1 upon 500. All right, this is the key idea of the parametric bootstrap. We simulate from the model under the null hypothesis. All right, and then in the t star b, we are going to compute that same test statistics, the sample mean minus 500 for the bootstrap samples, and store it in the vector t star. After the loop, okay, after the loop, t star contains an empirical approximation of the sampling distribution of the t statistics when h naught is true. After that, we are calculating the p value. Okay, in the p value, that will be the sum of t stars that are less than equals to t observed plus 1 divided by the b plus 1. All right. So this one, sum of t star less than equals to t observed, count how many bootstrap statistics are less than or equals to the observed observed test statistics t observed. All right. Then plus 1 in the numerator and denominator is a common adjustment. Sometimes we call it as the deviation Hinckley correction to avoid the p-value of 0 and to account for the Monte Carlo error. If effect, all right, and then we call the observed mean and we call the test statistics and we call the bootstrap p-value. All right, now we run it. So observed mean is 517.2. So test statistics is 17.2 and bootstrap p-value is 0.5844 0.5854. Okay, that is the bootstrap p-value and test statistics is 17.2. So what it means? Okay, it means that we are going to accept the null hypothesis at alpha equals to 0.05 because p-value is, sorry, p-value is 0.5854, that is greater than 0.05. So we are going to accept it. All right, we are going to accept the null hypothesis that mu equals to 500, right? Do you have any doubt till now here? The remaining part we will do in the next class. Okay.